Good morning, everyone. So, today we will explore some of the most fundamental um, and fascinating concepts of theoretical computer science and computational complexity theory, PNP, NP complete, and NP hard problems. So, first we will understand what is computational complexity. So, computational complexity measures how hard a problem is based on the resources. So it also makes us understand how long an algorithm takes, like time complexity. And space complexity, how much memory it uses. It usually expressed in terms of big of n, big of n square, big of 2n. So computational complexity, seeks to classify, which seeks to classify problems according to their inherent difficulty and according to this theory of problems intractability remains the same for all principal models of computations and all reasonable input uh, codings encoding schemes for the problem understand under consideration. We just touch on some basic notions and ideas of complexity theory in this section. So, first we will see P problems. What is P class? So, class P is a class of decision problems that can be solved in polynomial time by deterministic algorithms. This class of problems is called polynomial. The so these problems are solved in polynomial time, efficient, solvable hoti, and growth is manageable. So the restriction of P to decision problem can be justified by the following reasons. First, it is sensible to exclude problems not solvable in polynomial times because of their exponentially large output. Because of the large output, we cannot solve it. Such problems do arise naturally. Generating subsets of a given set or all permutation of n distinct items, but it is apparent from the outset that they cannot be solved in polynomial time. Second, many important problems that are not decision problems in their most natural combination can be reduced to a series of decision problems that are easier to needed to color the vertices of a graph so that no two adjacent vertices are colored the same color. We can ask whether there exists such a coloring of graphs vertices with no more than m colors for m is equal to 1, 2. The first values of m in these series for which the decision problem of coloring has a solution solves the optimization version of a graph coloring problem as well. So if like it is a natural question, like is every decision problem can be solved in polynomial time or not? So the clear answer turns out to be no. In fact, some decision problems cannot be solved by at all by any algorithm. Such problems are called undecidable as opposed to decidable problems that can be solved by an algorithm. So yeah. So now we will see the class NP, non-deterministic polynomial time. So a non-deterministic algorithm is a two-stage procedure that takes as its input an instance I of a decision problem and does the following. Non-deterministic guessing stage. An arbitrary string S is generated that can be thought of a candidate solution to the given instance I, but may be complete gibberish as well. Deterministic verification stage. A deterministic algorithm takes both I and S as its input and output. Yes, if S represents a solution to instance I. If S is not a solution to instance I, the algorithm either returns no or is allowed not to halt at all. We say that a non-deterministic algorithm solves a decision problem if and only if for every yes instance of a problem it returns yes on some execution. In other words, we require a non-deterministic algorithm to be capable of guessing a solution at least once and to be able to verify its validity. And of course, we do not want it to ever output a yes answer on the instance for which the answer should be no. Finally, a non-deterministic algorithm is said to be non-deterministic polynomial if a time efficiency of its verification stage is polynomial. So, what NP class problem is? A class NP is a class of decision problems that can be solved by a non-deterministic polynomial algorithm. This class of problems is called non-deterministic polynomial. P versus NP. So most decision problems are in NP. First of all, this class includes problems in P. This is true because if a problem is P, we can use the deterministic polynomial time algorithm that solves it in verification stage of a non-deterministic algorithm that simply ignores string S generated in non-deterministic stage. But the NP contains the Hamiltonian circuit problem, the partition problem, decision versions of a traveling salesman, knapsack graph coloring, and many hundreds of other difficult combinatorial optimization problems catalogued. The halting problem, on the other hand, is among the rare examples of decision problems that are known to be in NP. Note that P is equal to NP would imply that each of the many hundreds of difficult combinatorial decision problems can be solved by a polynomial time algorithm, although computer scientists have failed to find such algorithms despite their persistent efforts over many years. Yes. Now we'll see NP complete problem. So informally, the NP complete problem is a problem in NP that is as difficult as any other problem in this class, because by definition any other problem in NP can be reduced to it in polynomial time. A decision problem D1 is said to be polynomically reducible to a decision problem D2 if there exists a function T that transforms instances of D1 to instances of D2 such that T maps all yes instances of D1 to yes instances of D2 and all no instances of D1 to no instances of D2. T is computable by a polynomial time algorithm. This definition immediately implies that if a problem D1 is polynomically reducible to some problem D2 that can be solved in polynomial time, then problem D1 can also be solved in polynomial time. So, what is the definition of NP complete? A decision problem D is said to be NP complete if first it belongs to a class NP, and second if every problem in NP is polynomically reducible to D. Now NP hard. So, NP hard problems are the class of problems um, that are at least as hard as the hardest problems in NP. Uh, this means that if you had fast, efficient algorithm to solve a NP hard problem, you could use it to solve every problem in NP quickly. However, like NP complete problem, NP hard problem do not have to be in NP themselves. This means that their solutions might not be verifiable in polynomial times. Some NP hard problems can be even more difficult, possibly undecidable, where no algorithm can solve them in any cases. So examples are the halting problem, knapsack problems, scheduling problems. Summary is like P problem that can be solved quickly by an algorithm. The time to solve grows at most polynomically with input size. Example are sorting and searching. NP non-deterministic polynomial time problems for which a given solution can be verified quickly even if finding the solution is hard. Example Sudoku. NP complete. The hardest problems in NP, if you solve any NP complete problem quickly, they can solve all NP problems quickly. Famous examples are traveling salesman and scheduling algorithms. NP hard problems are at least as hard as NP complete problem, but may not be in MP. Some NP hard problems are undecidable. Example, the halting problem. The, okay. So, thank you.